In this video, we're going to look at differentiating between different types of mathematical models. So sometimes when you're looking at a graph or you're looking at some data, like a list of numbers, sometimes it's clear what kind of pattern you're looking at, and sometimes it's not clear what kind of pattern you're looking at. So telling the difference between these is really what we're going to be doing here. And the three types of functions we're going to use for that are linear, quadratic, and exponential. So by looking at the graphs, you should be familiar with these by now. When you're looking at a function or some data you think is linear, this is probably the one you're most familiar with in a sort of math class situation. It has this nice straight line, that's why it's called linear, and it's growing, it has a constant growth rate or a constant slope. When you're looking at quadratic, in this case it's increasing here, but the difference is that it's curved. That's one difference, is that it's actually curved upward here. Another difference is that there is a part of the graph where the function actually changed direction. So as we were moving to the right, from here to here, it's decreasing. The function is going down as we move from here to here. And then, once we get to this point, which is called the vertex, it starts increasing. And exponential growth, we have a upward curve similar to the quadratic one, but the difference is we don't have a vertex with exponential growth. It never changes from decreasing to increasing. It's just increasing all the time. So that's the main difference in telling between quadratic and exponential, is with quadratic you gotta look for a vertex. But the problem is sometimes and this is just a zoomed in version of this graph, I'm just taking the first quadrant and zooming in on that. If you look at it in this way, this quadratic graph looks an awful lot like this exponential graph. It's not clear because you can't actually see the vertex. You can't actually see that the function starts curving back the other way here. So sometimes it's good to be able to have some numerical ways to decide what type of data we're looking at as well. So let's get some numerical data for each of these functions. Okay, and linear and quadratic we've actually done before, but I'll review these quickly just in case. Linear, when we're trying to identify linear growth, we're looking for a common difference. If you're thinking about sequences, you can think about this as a common difference of an arithmetic sequence. It's basically the same thing, right? So what we mean is we're just subtracting a term from the previous term. Ooh, I said that wrong. We're subtracting the previous term from a term. So for example, if we want to know the difference between these two, we do the second number, 1.5, minus the first number, which is 1. And the difference is 0.5. And you'll notice that when we do the next difference, 2 minus 1.5, we again get 0.5. And same thing. 2.5 minus 2 is 0.5. And finally, 3 minus 2.5 is also 0.5. So we call it a common difference because the difference is always the same. In this case, it's always 0.5. So if you have that situation, that means you are looking at a linear function. For a quadratic function, if you just look at these numbers, you might be able to already identify that there is not going to be a common difference. But what's interesting is if we look a little bit further, if we look at the second difference, those numbers should be the same. So we'll find the differences between these first, just by subtracting like we did in the previous one. So that difference is 0.08. The difference between these two is 0.24. difference between these two is 0.4, and the difference between these two is 0.56. Okay, so these are not the same, which means it's not a linear function. What's interesting is when we find the difference between the differences, so for example, the difference between these two numbers, 0.08 and 0.24, is 0.16. Now if you find the difference between the next two numbers, that's also 0.16. And you find the difference between these two numbers, and it's also 0.16. So the point is, with a quadratic function, if you find the second difference, those numbers should all be the same. If you find some data where the second difference is the same over and over and over again, that means you're looking at some data that could be modeled using quadratic growth. Okay, so exponential. First, I'm going to show you that it's not linear and it's not quadratic. So if it was linear, we would have a common difference. So if I find a few differences here between these two, it's 0.3. Between these two, 0.39. And between these two, 0.489. So you can see already there is not a common difference. So it's not linear. Hopefully that's not too surprising for you. We could look for a second difference and see what's happening here. So the difference between these two is 0.09. The difference between these two numbers is 0.099. So even the second difference is not the same in this situation, which means it's also not quadratic growth. Even though they look quite similar, the numbers don't work exactly the same way. So for exponential growth, what we do is we use the concept from geometric sequences. That is, we try to find a common ratio. If there's a common ratio, that means we're multiplying by the same thing over and over again, and that's exactly what gives us exponential growth. Okay, so in this case, instead of finding the difference, instead of subtracting, what we're doing is we're dividing. So if I take 1.3 divided by 1, I get 1.3. If I take 1.69 divided by 1.3, I again get a factor of 1.3. Same thing here, 2.179, if I divide that by 1.69, I get 1.3. And again, for the last two numbers. Okay, so if you have a common ratio or a common multiplying factor to get from one term to the next term, that is a situation when we're looking at exponential growth. Well, let's take a look at this in terms of our coronavirus statistics. In this case, we're looking at the country of China. If you look at the graph of China, this curved part here appears to be some sort of exponential growth. So one thing we could do is check that and see if is it exponential or is it quadratic. A couple things I want to point out to you here. When you're looking at your graph, make sure that you choose linear here. If it's set to log, you're going to get a kind of weird looking graph because we're using a different kind of y-axis. So for now, just stick to linear. And if we want to know in this area here, we can restrict the dates. So we get a nicer picture like that. Maybe I'll go a little bit further. And to make it a little bit more smooth, we can use this 7-day rolling average feature, and that makes it nice and smooth. Okay, so I've already done this. I'm not going to go through the calculations one by one with you. What I found is the ratio between these 2 days I've calculated, and that is 1.43 about. The ratio between these 2 days is about 1.48. The ratio between these 2 days is about 1.43 again. And the ratio between these 2 days is about 1.39. So you might be arguing here, well, hang on a minute. These numbers are not exactly the same. There isn't a common ratio. And that's true. This is not exactly a geometric sequence. But because those numbers are all so close to each other, 1.43, 1.4, 1.48, 1.43, because they're all really close to each other, that means we can use exponential functions as a model. And I say model, I mean we're using something that gets us close to being a representative of this data, right? The point of modeling is not getting the exact answer. It's using some kind of simple mathematical tool so that we can get a rough idea of what's happening in the situation.